Hey everybody, today we're going to be discussing finite and infinite sets with me, and basically all that means is we're going to discuss how many elements are in a set. To start off that discussion, we are going to start with A and B are equivalent. So when they are equivalent, that just means that there exists a bijective function between A and B, and we denote this with a triple equal sign, and when they are not equivalent, we put a slash through that equivalent sign. So to start off, we are looking at A and we are looking at B, and we want to define a function that is bijective between the two in order to determine whether or not they are equivalent. So first thing that I'm going to notice is that we have like this 2, 1, 4, 3. So everything is just offset by 1, which is the case when you're talking about evens versus odds. So if we define a function from A to B, and I'm going to do it by f of x equals x, and then either plus or minus 1. So if I were to try 2, and I do 2 plus 1, that would give me a 3, and so I would have missed this element here in B. And so I'm not going to use plus 1, I'm going to decide minus 1. Now to prove that this is going to be one-to-one and onto, since it's a finite set, and it's really quick to just list everything and look at it, it is okay to actually just list it out. Again, this only works because it's finite. So f of 1 is equal to, f of 2 is equal to 1, f of 3, I cannot talk, f of 4 is equal to 3, f of 6 is equal to 5, f of 8 equals 7, f of 10 equals 9. Notice I did not do any sort of like dot, dot, dot crap. That does not fly if you are trying to prove that this is one-to-one or onto by listing things out explicitly. You have to list them out explicitly. So I can just say like clearly one-to-one. And onto, because we can see all of the elements B get mapped to, we can see that none of the elements A go to the same place. So we're good. This is a bijective function. B, or not B, F. F is bijective. So then we can conclude that A is equivalent to B. Now what I want to draw your attention to is like, what if we had had another element in B? Would we have still been able to do a bijective function? And the answer is no. Then we would have had 6 elements over here, and so somebody wouldn't get mapped to, because we can't have like one of these elements splitting off and going multiple places. If we'd had like another element here, then and no 6th element over there, then we would have 6 over here, and then we would have had to have something doubling up and going to the same place. Otherwise, we wouldn't be able to use all of the elements in our domain. So the fact that they had the same number of elements is really important. Which brings us to the notion of cardinality. We say that cardinality for a finite set is just the number of elements in the set. We denote that using like this absolute value symbol, or you could use card of A. Just so you know, your book does this, and that is truly hideous. I don't know what they were on when they decided to write that. Nobody uses that. But let's take this for a quick run. Let's think about the cardinality of A. I can sit here and count these elements. There we go. I have found that they have 5 elements. So we say the cardinality of A is going to be 5. So how is this related to what I said before? Your book does a very convoluted, notationally heavy explanation of this. But what I did was I defined a bijection basically between the set 1, 2, 3, 4, 5 and the set A. And that's really all counting is a bijective function. Congrats! If I were to like try and count the number of spoons that are in my house, if I didn't count one or I missed it, then I wouldn't have counted all the spoons in my house. I would have failed at counting. I've miscounted. That would be the same thing as not having an onto function, because I've missed something. I've missed one of the elements. If I were to accidentally double count one of my spoons, then I would not have a one-to-one function because something has been counted twice. So again, that would be miscounting. So as long as you're counting correctly, that is a bijective function. And so I don't really want you guys to get bogged down in trying to develop bijective functions to count finite sets. If it's finite, you can count it because you have fingers and we're not in preschool anymore. But on that note, you've been dealing with bijective functions since you were in preschool, so congratulations. Moving on, now we can talk about like, what if we start like gluing some finite sets together, like what's going to happen? Part A of this theorem, I think, is very easy to think about. Like if you have A and B are both finite, so like A has 7 elements, B has 3 elements, and they don't overlap, then that's what disjoint means. So A and B don't overlap. Then when you put them all together, you're going to have 10 different elements. And the proof for this is just not insightful. How do you spell insightful? Not insightful. And so we are not going to go over it. It's a trivial concept to think about, but not a trivial thing to prove. And so we're not going to mess around with that. I think you guys get it. Part B, however, this one's kind of fun. So notice when we don't specify the disjointness, so in part B, they're just finite sets, we don't get quite so simple a formula, but it does still make sense like intuitively, because if you have A and you have B and there is some overlap here, then if we count all of A and then we count all of B, we're going to have some overlap. And so we've counted things twice. And so what we have to do is get rid of one of those intersections so that we don't have it showing up twice. So in order to do this, we want to be able to apply this, which means we need to develop a way of writing A union B using disjoint sets. Just by definition of what it means to the difference of sets, remember like A minus B, we could do A like minus B, or A backslash B would be the better notation. So A without B is going to be disjoint from the part where A and B overlap. So union A intersect B. And then to get the rest of the union, we need all of this, all the parts of B that we haven't counted yet. So that would be A union B minus A. So these guys here are disjoint, which means we are now free to try and make use of the first part of our theorem. So let's flip to the next page. We can say that the cardinality of A union B is going to be equal to A minus B plus A intersect B plus the part from B minus A. Okay. Again, because they're disjoint. So that's what? Theorem 5.17a? Cool. Now, what we have is the cardinality for A minus B, but really we wanted the cardinality for like just A. So let's look at our drawing again. This is A. So A is made up of this part. So A is equal to A minus B plus the part that did overlap with B. So it's going to be union A intersect B. Then I don't know, I may have had you prove maybe this one previously, I may have not, but it's a pretty trivial thing to prove, so, or not trivial, but simple thing to prove, so we're not gonna mess around with that right now. we're going to take me at my word. But again, disjoint sets. So now we can talk about the cardinality of A and say it's going to be A minus B plus A intersect B. And now these are all numbers. That's all cardinality is. So we can rearrange this and get information for A minus B. There we go. Now we're going to do the same thing for B minus A. So we could say that B is equal to B minus A union with the intersection. So that would be like, this is B minus A, and then the intersection. Again, disjoint sets. We get to make use of our theorem. And then we're going to solve this for B minus A. Okay, and then I'm going to make room for myself to cite the theorem because I'm proper like that. There we go. Now that we have expressions for B minus A and A minus B, we can go ahead and plug those in from before. So then A union B will be equal to A minus A intersect B plus A intersect B plus B minus A intersect B. So like a more proper way to notate that, star implies. And then we can simplify this. A plus B minus A intersect B, because like these ones canceled out, if you will. And there you go. We have proven our theorem. Whee! And then part C is going to be, remember that's this infinite, or not infinite. This is a bigger union, and you can prove that one by induction. And I've left that one for you to do on your homework. You're welcome. So that's all I have for you guys right now. Big ideas today are cardinality, which is how many elements are in a set, and a couple of quick results. We're going to dig into different types of infinite sets next time, and I'll see you guys then. Bye.